Tell you that the square root of minus g mu nu semicolon lambda equals 0. So we've got two equations of motion. One comes from setting to 0 the coefficient of delta G. The other comes from setting to 0 the coefficient of delta gamma. So we're almost there, because this equation is equivalent to d gamma G beta gamma minus G gamma sigma beta lambda minus G beta sigma gamma lambda equals 0. And we can solve, and no prizes for guessing what the answer is. It's the one we've been using all along. So this is the familiar equation relating gamma to G, but we didn't define it that way. Instead, it emerges as the equation of motion you get from varying gamma. In analogy with what we did in the Maxwell case, where the relation between F and A was the equation of motion you get by varying with respect to F. So once again, the physics is the same, and which formalism you adopt is a matter of convenience. But the subtlety comes when we couple to matter, which is what we're going to do now. And if your coupling to matter involves only G, then whether you do first or second order formalism gives you back the same answers. The subtlety would be if you were, and it's debatable whether this is a good thing to do or not, but if you were to couple gamma to matter as well as G, then the two approaches would diverge and give you different physics. So let's couple to matter now. That's what we're going to do next.
Hi.
Yeah?
Sorry. What exactly do you mean by coupling gamma to matter independently of coupling G to matter?
I'll elaborate on that in just a few minutes when
Okay.
You see, let me anticipate a little bit. Our recipe for going from flat space to curved space was to replace eta mu nu by G mu nu and replace ordinary derivatives by covariant derivatives. And covariant derivatives involve gamma. So you might say, well, of course, gamma couples to matter. But in most of the examples we like, it turns out that the gammas cancel out. For example, I'll show you now that in the examples we like, we can replace the covariant derivatives by ordinary derivatives and get the right answer. But we'll see how that works now. So, next section is the energy momentum tensor. This is 4.4. Now, what's usually called the Einstein-Hilbert action, which was the subject of section 4.1 or 4.2, is just the gravitational part of the story. But of course, to do physics, we want to couple gravity to other fields. So from a variational point of view, we want to augment what we did before to include matter. And we denote this by S of G and psi, where psi, for the moment, is some generic field. Could be a Maxwell field, could be a scalar field. We're not going to, could be a point particle or something. We're not going to specify for the moment what it is. We'll do that later. So now we're going to have an action principle that will be a sum of the gravitational part, which depends on G, part we've already discussed. And we're going to add to it a matter part, which will depend on psi and on G. Where, as before, the gravitational part is what we've already discussed. And I'm going to be working in conventional second-order formalism from now on. And Sm of G and psi will be the integral d4x of some Lagrangian density, which we call L sub m. And I'll be giving you specific examples of what that Lagrangian is, but let's leave it generic for the moment. So we vary with respect to G and I'm going to put in a factor only 2 kappa. Delta G mu nu. and delta SM will be a sum of two terms. One, and let's suppose this matter field has some index I, could be a mu, could be some internal index. Again, it's generic, just some set of fields, psi I. So delta psi I is going to take this form, and we're going to call what sits in here minus 1/2 T mu nu. And we're going to call what sits in here x I. And these objects, T mu nu and xi, will depend on the details of the Lagrangian. But we can read off what the equations of motion are. By setting to 0 the coefficient of the variation of delta G, we get the Einstein equation with now a right-hand side. And the equation for psi will be the vanishing of whatever sits inside this bracket there. And so we identify T with the energy momentum tensor. In fact, from this perspective, one can define the energy momentum tensor to be whatever sits in that variation. Yeah?
There's a minus sign in front of kappa.
Where? Here?
Yeah.
I'm reluctant to say kappa is minus 8 pi g. Remember.
And there's a minus sign in front of the action of gravity. So you get the Einstein tensor plus the energy momentum tensor equals 0.
Yes. My Lagrangian is 1 over 16 pi g integral g4x square root minus r. So there's a minus sign here, which compensates for the minus sign there. Now, it's conceivable that in going between Weinberg and Anderson, there's some convention in the sign of the Riemann tensor. So I'll check on, I'm not going to check that now. Section 4 will be internally consistent, I guarantee that. But there may be some minor sign conventions between earlier sections, which I'll check. Yes?
Well, you can see that if you set the coefficients of delta G equal to 0, there would be a minus sign somewhere.
You change the
Oh, have I
definition
done
of
something
managed momentum
inconsistent?
There's a minus at the front of delta SG.
Oh, that should be a minus kappa, you're saying.
You can redefine the image momentum tensor.
You add them, right?
Change
So my promise that it was internally inconsistent is under threat. Let me see. There's a minus here,
Yeah.
and there's a minus there. So, yes. I've lost a sign somewhere, haven't I? Let me not attempt to chase it up now.
Change the definition of energy momentum tensor. Because you don't need the minus.
I'm sorry, I can't hear you. Could you?
You set the minus 1/2 to plus 1/2. Then it will.
If we do that, everything's okay, yeah. But I want to make sure that that doesn't spoil some other equation. It's conceivable that I've combined a Weinberg convention with an Anderson convention. So I'll sort that out for tomorrow. Let's carry on, subject to this possible sign ambiguity. So let's look at some examples. And the first one is point particles. With masses m sub n. So we're going to look at n point particles with masses n sub n, trajectories x mu of p, and we're going to give them a subscript n. So x1 will be the trajectory of particle 1, x2 will be the trajectory of particle 2, and so on. And Sm, in this case, will be minus the sum over n, m sub n, integral minus infinity to infinity dp, g mu of x sub n, dx mu sub n, dx mu sub n, dp, dp to the 1/2. And you can, I will leave it as an exercise. To show that the equations are g mu nu is minus 8 pi g t mu nu, where t mu nu equals 1 over the square root of minus g, the sum over n m sub n integral minus infinity to infinity ds sub n dx mu sub n ds n dx nu sub n ds n times the four-dimensional delta function x minus x sub n. That's the Einstein equation. And the equation we get by varying with respect to x is d2 x mu sub n dsn squared plus gamma mu rho sigma dx rho n dx sigma by dsn dsn. So the varying with respect to g, we get the Einstein equation with the energy momentum tensor of the point particles on the right-hand side. Varying with respect to x, we get the geodesic equation of motion. Now, what we normally do, well, what we did when we were looking at bending of light and the perihelion of Mercury and so on, we focused on this in some solution of this, but we ignored the effect of the T mu on the gravitational field, which is a good approximation. The existence of the planet Mercury on the sun's gravitational field is negligible, so it was a good approximation. But that approximation where you focus on this as a solution of this, but ignoring the back reaction of the matter on the gravity, that is called the what's it called? The test particle approximation. That's the word I was looking for. We treat it as a test particle and ignore the reaction back on gravity. So let's look at a second example. The simplest example is the scalar field. So it's a single scalar field which we call phi of x. S of g and phi will be sg of g plus sm of g and phi. And sm of g and phi is 1/2 integral d4x root minus g Now the rule is to replace ordinary derivatives by covariant ones, but for a scalar it's the same thing, so these are just ordinary derivatives. and we're going to give the scalar field a mass m. Now, why is that the Lagrangian? Well, it's what we want to get is the Klein-Gordon equation, and that's what we need.
What does it mean for a scalar field to have a mass?
Well, that's a very topical subject because they've just discovered the first ever elementary scalar particle, at least they think it's a scalar particle, at the Large Hadron Collider. And it has a mass of 125 GeV. And that's determined by the, how do they know it's got a mass of 125 GeV? You look at the collision process, you assume conservation of energy and momentum. You look at the energy of the decay products, and going backwards, you determine that it has a rest mass of 125 GeV. So that's what it means for a scalar field to have a mass. It's an elementary particle. And elementary particles are either massless and travel at the speed of light, or they're massive and travel less than the speed of light. And I'm looking at the massive case here.
In the second action, which kind of metric do you use? The minus 1 or 1 minus 1?
The other one.
1.
The other one.
Mostly negative.
Yeah.
I think I've switched to
Switch.
1, minus 1, minus 1, minus 1. I promised you this would be internally consistent, but not necessarily consistent with. So, yes. If this, in the other metric, there would be a minus sign here. My apologies for the mixing of conventions, but it's a matter of when you use more than one textbook, that's an inevitable danger. Now, let's vary with respect to phi. Not sure why I've got two halves there. Yeah. I think this is correct. Yes, I know why. I'm going to be using delta root minus g is 1/2 root minus g, g mu nu, delta g mu nu, and delta g mu nu is minus g mu rho, g nu sigma, delta g rho sigma. So we plug that into there, and what we get are several terms. It's strange, as theoretical physicists have been writing down Lagrangians for scalar fields for years and years and years. But it's only a couple of weeks ago that we were justified that there is indeed an elementary particle with spin 0. Although, to be fair, they haven't yet confirmed that it's spin 0, but it's 99% sure that it is. Scalar and spin 0 are synonymous, by the way. Scalar is spin 0, spinor, spin half, or spin 3 halves. And vector is spin 1, and the graviton is spin 2 in this language. So we can read off from this the energy momentum tensor and the equation of motion for the scalar. And the equation of motion, after integrating by parts, is g mu nu grad mu d mu phi plus m squared phi equals 0. And this is named the Klein-Gordon equation. It's a curious quirk of history that the Klein-Gordon equation, which is a relativistic equation, was written down before Schrödinger wrote down his non-relativistic equation. And at the time, people were upset that Schrödinger's equation wasn't relativistic. And yet it's Schrödinger's equation that turned out to be the more important one. Yeah?
Why is there one covariant derivative there and another one just being the partial? Because that acts on the, I mean...
Yes, this is the same thing. As this. Because when it acts on a scalar,
Yeah.
I can swap d with d, same thing. But when it acts on a vector, which d nu phi is, I can't. So I have to, the first one has to be covariant. The second one, you can choose, it's the same thing.
Yeah.
So there's a strange history with the Klein-Gordon equation. It predates the Schrödinger equation, but the Schrödinger equation turned out to be the more useful one for quantum mechanics. But this is the equation in quantum field theory that you need to describe a spin 0 particle. And this is how you couple it to gravity. Let's look at another example, the Maxwell field. apropos of what we were just saying about covariant derivatives, they're both ordinary ones here. It's enough. But if we were to integrate by parts and throw the derivative onto the phi, then we'd have to have a covariant one. So the next example is the Maxwell field. Now there's a minus 1/4 integral d4x. So we follow the same prescription, replace Minkowski metrics by Riemannian metrics, and ordinary derivatives by covariant ones. But once again, we don't need the covariant derivative because the curl of a vector is the same thing. The gammas cancel, and the only derivatives we need in the Lagrangian are ordinary ones. So that's an example of what I was mentioning before, that although the rule is to replace ordinary derivatives by covariant ones, so far we haven't needed the gamma in the Lagrangian, the matter Lagrangian. So you do the same business. I won't bother to go through it. The T mu nu is minus F mu alpha F mu alpha plus 1/4 G mu nu F rho sigma F rho sigma. And the field equation, where I do need the covariant derivative, is this. So tomorrow we'll finish off, I think, the section on the Lagrangian formulation, and then Thursday and Friday will be cosmology. Any questions?